Dear students, today's topic is geometrical symmetry. What is geometrical symmetry? Suppose there are certain objects which undergo certain operations on it. The operations may be changing the position of that object, changing the place of that object, or there may be some rotation motion given to the object, or some work is done on the object. These are nothing but the operations done on the object. In that case, if the object retains its original conditions, even if some operations are done on it, still it retains its original conditions, then the body is said to be symmetric. Such a body or such an object is said to be symmetric. The operations or the performances that are done on the object or the body are change in place or position, the rotational motion given to the body of the object, or some work done, and so on. Now, depending on these operations performed on the body, there are three types of symmetries. They are time translational symmetry, translational symmetry, and rotational symmetry. These are the three symmetries depending on the operations performed on the body. And the law of nature, what it says is, physical laws do not change with time. This is called time translational symmetry. It also says, physical laws do not change with position or place. This is called translational symmetry. Another one, physical laws do not change with direction. And this symmetry is called rotational symmetry. And these are the three laws of symmetry: time translational, translational symmetry, and rotational symmetry, depending on the operations. First one, laws do not change with time. Second one, laws do not change with position or place. Laws do not change with direction or rotation. Based on these symmetries, three laws are proposed. There are three laws of nature. They are law of conservation of linear momentum, law of conservation of angular momentum, and law of conservation of energy. This law of conservation of linear momentum associated with translational symmetry. Law of conservation of angular momentum, it is associated with directional symmetry or rotational symmetry. And the third one, conservation of energy, associated with time translational symmetry. And now our topic is, let us consider the first one, law of the first symmetry, law of conservation of linear momentum. The symmetry is translational symmetry, and the associated law is law of conservation of linear momentum. Now, what is linear momentum? You have studied these things in your PO class. A body in motion possesses quantity of motion. This quantity of motion possessed by the body in motion is called momentum. Linear means the motion is always along a straight line. Whenever a body is in straight line motion, it is in translational motion, motion along a straight line, translational, motion along a straight line. The quantity of motion possessed by the body is called linear momentum of that body. And we measure momentum as the product of mass and velocity. Momentum denoted by P, given as the product of mass and velocity of that moving body. Here momentum is a vector, velocity also a vector. So momentum is given by mv vector. P vector is mv vector. More is the velocity, more will be the quantity of motion possessed by the body, or more will be its momentum, linear momentum. And Newton's laws, first law, second law, third law, already you have studied these things also. What second law says? The rate of change of momentum of a body is directly proportional to the applied force. What is force? F equal to mE. As from that law, we get the expression for force as F equal to m into A. M, mass of the body, A is its acceleration. So force is defined as the agent which overcomes inertia. Inertia, the tendency of the body to remain in the same state, is called inertia. The one who overcomes inertia is the force. So that whenever force is applied, it overcomes inertia, body gets accelerated given by with an acceleration set A, so that F equal to ma. What is acceleration? Rate of change of velocity, dv vector by dt, dv vector by dt. So that F is m dv by dt, or m is a constant, you can take inside. So that it is d by dt of mu vector, m is nothing but momentum, so that force is nothing but dp vector by dt. So we define force also as rate of change of momentum. Force is also defined as rate of change of momentum. Suppose the applied force on a body is 0, that is F0, that implies dp vector by dt is 0. This derivative is 0 means the quantity that should be constant. Then only this derivative becomes 0. So that p vector is a constant. P vector constant, linear momentum is constant, and this is called as conservation of linear momentum. This is how you can show that when in the absence of the applied force, momentum of the body remains constant. That is, momentum is conserved. Conservation of linear momentum. The conservation of linear momentum also states that the total momentum possessed by a body always remains constant before it undergoes some operation and also after that operation. Suppose the body possesses certain momentum and then after that it undergoes some operation. After that operation also, if the momentum remains same, in that case we say that the momentum is conserved. This is nothing but conservation of linear momentum. Momentum cannot be created anew or it cannot be destroyed. We can't give momentum to the given body after the operation, or momentum cannot be removed from that after operation. This is called conservation of linear momentum. And this conservation of linear momentum is the working principle of a rocket. What's a rocket? It's a satellite launching vehicle. Satellite launching vehicle. Rocket is the satellite launching vehicle. And the working principle is conservation of linear momentum. Here, the fuel, either liquid fuel or solid fuel, it burns in the combustion chamber. Burning of the fuel takes place in the combustion chamber. See, this is the schematic diagram of the rocket. This is the top face of the rocket. This is the tail. This is the head part. This is the tail part. In the combustion chamber, see, the rocket will be in this shape. The shape is called the streamline. The shape of a streamlined body. So here in the chamber, burning of the fuel takes place. Burning of the fuel leads to production of the gases. Gases are produced inside. Those gases, they escape from the nozzle in the tail. There is a nozzle, they escape through that nozzle. So here, the principle is jet propulsion. Working principle is conservation of linear momentum and also jet propulsion. Jet propulsion means oozing out or escaping of gases with a very high momentum through the tail of that rocket. So the working principle of the rocket is jet propulsion and conservation of linear momentum. Now let us discuss or let us find out the expression for the final velocity of a rocket using the law of conservation of linear momentum. Here we have a rocket. Here it is assumed that during the motion of the rocket is moving upward, the gases are escaping in the downward direction. Here it is assumed that air resistance offered is negligible and the gravitational force of attraction is also considered to be negligible. Using these two assumptions, by assuming these two things, let us derive the expression for maximum velocity attained by the rocket. Let m0 be the initial mass of the rocket before moving when the rocket is at rest. Let m0 be its mass. That m0 is taken as mr plus mf. Mr, mass of the rocket, the empty rocket without any fuel. Mr, mass of the empty rocket without any fuel. Mf, the mass of the fuel that filled inside the combustion chamber. So total mass to start with m0 initial when time t equal to 0 before the rocket flies. m0 is mr plus mf. Let v be the velocity of the rocket. Suppose the rocket flies and moves up. Let v be the velocity of the rocket at any instant after launching. It is launched. The rocket is launched from the launching pad after launching, after the time instance set t, let v be the velocity of the rocket. It is moving upward. V be the velocity of the rocket with respect to the earth. Remember, v the velocity of the rocket with respect to the earth. Here, how the rocket moves are, when the gases, they are leaking or they are escaping from the nozzle, the very high momentum in the downward direction and equal momentum of these gases. The momentum equal and opposite to that of the gases is transferred to the rocket, so rocket moves upward. Gases are coming downward and the rocket is moving upward with equal momentum. Momentum of the rocket is equal and opposite to that of the gases coming through that nozzle in the downward direction. Let u be the velocity with which the gases are escaping. Velocity of the gas escaping. Velocity of the gas with respect to the rocket. U the velocity of the gas with respect to the rocket. So that velocity of the gas now with respect to the earth. Now let us consider the velocity of the gas with respect to the earth. It is taken as velocity of the rocket with respect to the earth, that is v, plus velocity of the gas with respect to the rocket, that is u. So v vector plus u vector. Or it is any vector quantity product of magnitude and the unit vector. Let n cap be the unit vector. So that v vector is v n cap, u vector is u minus n cap because u is opposite to v. So the unit vector is taken as minus. So that from this we get velocity of the gas with respect to the earth as v minus u n cap. Now, as time increases, mass of the rocket goes on decreasing. Along with that, whereas the mass of the gases, escaping gases, goes on increasing. So there will be change in the mass of the rocket with the time. That rate of change of mass of the rocket denoted as dm by dt. Let dm by dt be the rate of change of mass of the rocket. That dm by dt, rate of change of the mass of the rocket, which is decreasing one. Dm by dt is decreasing. With that, so that the mass of the escaping gas increases, so that increase in mass we denote it as minus dm by dt. Minus dm by dt represents increase in the mass of the escaping gases. Now, let m be the mass of the rocket at any instant t. At any instant t after launching, m be the mass. So that momentum, linear momentum of that rocket now moving with the velocity v. So by definition it is mv n cap. Now let us consider the change. Rate of change of momentum of the rocket now. So remember here we are talking about that of the rocket. Its mass at an instant, let it be m. After it has decreased from m0 to m. Then its momentum is mv n cap. Rate of change of momentum is we differentiate d by dt of mv n cap. Here both m and v are variables. Velocity changes, mass also changes. So both are variables. Differentiate. Product rule again. Apply product rule. So it is dm by dt into v plus m into dv by dt into n cap. N cap is common. Product rule. Differentiation of the first factor into the second plus first factor into differentiation of the first. So we get equation 1. This equation gives rate of change of momentum of the rocket. Now let us consider rate of change of momentum of the gas, because the change in momentum of the gas is transferred to the rocket to move it, to take it in the forward direction. Rate of change of momentum of the gas now. As I told, dm by dt, rate of change of mass of the rocket, it is decreasing, so that minus dm by dt represents rate of change of mass of the gases, which is the increasing value. So that rate of change of momentum of the gas is given by change in mass minus dm by dt into velocity of the gas, escaping gas with respect to earth. Here we have it as v minus u n cap. So that this is rate of change of momentum of the gas. Here the working principle is rate of change of momentum of the gas, rate of change of momentum of the rocket is equal and opposite to that of the gas. So that rate of change of momentum of the rocket is equal to this but opposite. This is equal to this but opposite. So minus rate of change of momentum of the gas. That is minus of this term. So this minus becomes plus. We get rate of change of momentum of the rocket as dm by dt v minus u n cap. Or instead of this, let us simplify. What this becomes? dm by dt v n cap minus dm by dt u n cap. Let this one be equation 2. Now using equations 1 and 2. See, both 1 and 2 are the expressions for rate of change of momentum of the rocket. These two give the rate of change of momentum of the rocket. Now equating those two. From these two, 1 is equal to 2. Now let us write. Both are rate of change of momentum of the rocket. So 1 is equal to 2. 1 equal to 2 implies first one is dm by dt v plus m dv by dt whole n cap. That is equal to, see here, dm by dt v plus, minus dm by dt u n cap common and keep it outside. So we get equating the two. We get these two. dm by dt v minus dm by dt u. Equate these two. Now simplify. N cap cancels. Say first term dm by dt v. There also we have dm by dt v. If you take this term to the left hand side, it becomes minus. The net value is 0. So that what's remaining? M dv by dt is equal to minus dm by dt u. Or dt gets cancelled. Remaining m dv is equal to minus u dm. This is remaining. Or from this you can write dv as dv equal to minus u dm by m. This is the expression for change in velocity with change in mass. When the mass changes at the rate of dm, the velocity changes at the rate of dv. Now integrate both sides. Integrating both sides, we get left hand side, you get v is equal to minus u is constant. Remember, u is a constant. It is a designed value. The velocity of the gas is expelling gas. It is designed, so u is taken as a constant. U integration of dm by m. Now integrating that. Here we have v equal to minus u dm by m. Sorry, integrate this. Let us integrate and write. Integrate both sides. I write there, left hand side is v is equal to integration on the right hand side minus u, it's a constant, minus u integration of dm by m, it is ln m log with base e plus a constant of integration. Integration of dm by m, it's ln m or log with base e, Neperian base. U ln m plus c. C constant of integration to get c. Apply initial condition. When t equal to 0, v is equal to 0, m equal to m naught. To start with, these are the initial conditions. T0 to start with. Velocity of the rocket 0. It is at rest. Total mass is mass of the fuel plus that of the rocket. So m naught. Then what you get? V is 0. It is 0 is equal to minus u ln m naught plus c. Giving c as, get this side, u ln m naught. Therefore, substitute here. Substitute this one here. You get v is equal to minus u ln m plus u ln m naught. Or so the form u ln m naught minus ln m. Also the form u ln a minus ln b. You have the rule log a minus log b is log a by b. Log a minus log b. Log of a by b. Apply that. This becomes ln u ln m naught divided by m. Or v is equal to u ln, what is our m naught? It is m r, mass of the rocket plus mass of the fuel and divided by m. Thus, the general expression for final velocity of the rocket at any instant t is given by u ln mr plus mf by m. This is the expression. How v can be made maximum? How this v can be made maximum? As I told, u is a constant. Design value is a constant. It is fixed. For a given design, u fixed. So to change v, one has to change m, or one has to change mr plus mf. So v depends on mr plus mf and m. One can increase v by decreasing m. When m becomes minimum, the mass of the rocket becomes minimum, v will be maximum. Or mr plus mf, that should be maximum. Now, to make v maximum, v maximum if m is minimum. M minimum means this is m minimum possible is mr, because when the fuel is completely exhausted, the mass of the rocket, it is minimum mr, and further reduction is not possible. We can't reduce the mass further because mr is fixed one, mass of the empty rocket. As by reducing mf to 0, one can minimize the mass. So m minimum possible is mr, so that in that case v becomes maximum. V maximum it will be u ln m minimum equal to mr, substitute mr plus mf divided by mr, or from this we get v maximum is equal to u ln mr by mr 1 plus mf divided by mr, and this is the expression for the final velocity of the rocket, that the maximum velocity attained by the rocket, and v maximum depends on mf and mr. If you increase mf by mr, if that ratio is increased, mf by mr is increased, velocity is also increased. So one can increase the velocity by increasing this ratio. That mainly depends on either decreasing mr or increasing mf. This is the expression for final velocity of a rocket. With this, I stop here. Let us continue the remaining part of this in the next class.